Welcome. Today, we're going to take a careful look at two of the most fundamental ideas in Rust: variables and the data types that give them shape. By the end of this lesson, you'll understand how Rust stores values, why the compiler cares so much about types, and how this makes your program safer and faster. Let's begin. In Rust, you create a variable with the let keyword. By default, every variable you declare is immutable. That means once you bind a value to a name, you cannot change it. If you try, the compiler will politely refuse. This isn't a limitation, it's a feature. Immutable values make your code easier to reason about and help the compiler catch mistakes before they happen. When you do need a value that changes, you opt in with the mut keyword. This tells both the compiler and anyone reading your code that this variable is meant to be modified. Rust's philosophy is simple: make the safe path the default and make change explicit. Constants are a little different from variables. You declare them with the const keyword, and you must always annotate their type. Constants are evaluated at compile time. They're valid for the entire lifetime of your program, and by convention, we name them in screaming snake case. Think of constants as truths that never change: the speed of light, the maximum number of players in a game, the number of seconds in a minute. If a value is known ahead of time and will never shift, a constant is the right home for it. Rust has a quiet, powerful feature called shadowing. You can declare a new variable with the same name as a previous one, and the new binding simply shadows the old. Unlike marking a variable mut, shadowing lets you change the type of the value while keeping the name you started with. This is useful when you want to transform a piece of data, perhaps from a string into a number, without inventing a new name for each step. Let's talk numbers. Rust has two families of integer types: signed, which can be negative, and unsigned, which cannot. The sizes are named after their width in bits: I8, I16, I32, I64, and I128, alongside their unsigned counterparts, U8 through U128. There are also isize and usize, which match the pointer width of the machine you're running on. When in doubt, reach for I32. It's the default, it's fast on modern hardware, and it's what Rust will infer when you don't say otherwise. For numbers with fractional parts, Rust gives you two floating point types, F32 and F64. Both follow the IEEE 754 standard. The default, F64, offers double the precision of F32, and on modern CPUs, the performance difference is negligible. Addition, subtraction, multiplication, division, and the remainder operator all work just as you'd expect. Just remember, floating point math is inherently imprecise, so avoid it when exact values matter. Two more scalar types round out the basics. A bool is either true or false, a single bit of truth, stored in a single byte. A char represents a single Unicode scalar value. Unlike many languages where characters are just bytes, a Rust char is 4 bytes wide, meaning it can hold any letter from any language, mathematical symbols, or even emoji. Use single quotes for a char and double quotes for string literals. Now we move from scalars to compound types, types that group multiple values into one. The first is the tuple. A tuple has a fixed length, and each position can have its own type. You can destructure a tuple to pull out its pieces or access individual elements by their index with dot notation. Tuples are perfect when you want to return more than one value from a function without ceremony. Rust's other compound type is the array. Unlike a tuple, every element of an array must have the same type, and the length is fixed at compile time. Arrays live on the stack, which makes them extremely fast. If you need a collection that can grow, you'll want a vec instead, but we'll save that for another lesson. For now, know that arrays are your go-to for small, fixed-size sequences. And that's our tour: variables, mutability, constants, shadowing, the scalar types, and the compound types. Small ideas, carefully fitted together. In the next lesson, we'll put them to work. Until then, happy coding.